I'm going to introduce our work, no pens, more gains, recycling sub-salient patches for efficient image recognition. In high-resolution image recognition, downsampling brings a reversible information loss, while the original image incurs extreme training costs, and it could be summarized as the detail cost trade-off. And to address it, single buffer storage have been proposed. It selects a few high-scoring patches as the silent ones into a static buffer for aggregation, prediction, and optimization, while discarding the remaining sub-silent ones for no training consumption. As the foundations, some important works utilize independent score models to identify the most silent patches from downsized images and then fill their high-resolution counterparts into a static buffer with fixed capacity. The full resolution patches will then be encoded and aggregated for the final classification. Based on then, the follow-up researchers further extend the patch selection process in single buffer strategy into a multi-level one to achieve end-to-end training on more huge images, in which the identified silent patches at each resolution level serve as the candidates or inputs of the next level. To address this, IPS transformer employs local multiple instance learning architecture for patch scoring as well as aggregation, in which the gradients from the aggregation process are responsible for the optimization of ML and thus allows patch scoring in no gradient mode, and the local computational character further enables decomposing no gradients scoring process into iterative steps, thereby realizing efficient patch selection on high-resolution images with limited cost. However, in many complex scenes, using only a small number of regions cannot achieve correct recognition and training, but introducing more regions during training will also lead to an cost increase. So there is a problem, context loss or high training cost. Which one should we choose, or we can take it both? I call this issue as the context cost trade-off. And to address it, we propose a dual buffer strategy. We still use only a few silent regions for backpropagation, but introducing more sub-silent ones during the forward propagation to correct the gradients. And to suppress the backgrounds inside sub-silent patches, we devise a dual attention ML to generate a silent query for the aggregation of sub-silent embeddings. Finally, we introduce the random patch drop to reduce the patches that need to be traveled and uncover more informative patches. And the experimental results on 6 HRIR datasets have demonstrated the effectiveness and efficiency of our method. The ablation experiments has also proved both the effectiveness and the efficiency of each component in our method, while proving that our method will not bring a significant inference cost increase. And it's over. Thank you.